convex set? A convex set is any set such that if you draw a line segment in that set, the line segment should lie completely within the set. So that said that if you draw a line segment, that line segment should have the weighted average bundle being preferred. But this says that whatever line segment you draw, it should lie completely within the set. So take an example. Suppose I tell you I'm talking about a circle. And I tell you that my circle has this as the shaded region. This is my set. Whatever comes inside the circle is my set. Supposedly I tell you this. And I ask you, is this a convex set? So what's the best way to find out? You take any 2 points, you join it with the line segment. The line segment lies completely within the set. So yes, it is a convex set. But now, suppose I tell you that, you know what, this is a complete universe. I draw a circle in it, and now I am shading everything except the circle. So except circle, everything is shaded. This is your set. And I ask you, is this convex set? You will again think, you take any 2 points, line segment, points, join it with the line segment. The line segment is not within the set. It goes outside the set also, because it takes those points also, which is not a part of the shaded region. So is it a convex set? No. You can take various examples. Supposedly this is my triangle and this is my set. And I ask you, is this a convex set? You take any 2 points, join it with a line segment. Yes. Now think about this. I am saying that I have this circle as one of the set, but the boundary of the circle is not included. So I'm shading everything inside the circle, but not the boundary of the circle. And I'm asking, is this a convex set? So you take any 2 points, join it with a line segment, and the line segment point can lie on the boundary. It is not a convex set. Now for us, why this becomes important is because our indifference curves, which are well defined, are actually convex sets. How? Because if I draw my indifference curve,
ma'am.
Yes.
Ma'am, can you explain the last example of convex set?
Okay.
I can't get it. Yes.
So basically what we are doing is, we are taking a circle, but we are not including the boundary of the circle. So usually whenever we shade regions, you will do it in inequalities. Shading is always related to inequalities. So for example, you may have x minus a whole square plus y minus b whole square is equal to radius. This is the equations of the circles that we have, where a and b are the center point of the circle. So if my center is the origin of the circle, it becomes x square plus y square is equal to radius square. This is the equation. Now shading means that you don't have an equal to sign, you have a less than sign or a greater than sign. And then we say that, okay, what you have to do is you have to put x is equal to 0 y is equal to 0, and if it is true, then you will shade towards the origin. Otherwise, you will shade away from the origin. This is all maths. You will do it in maths in detail. Now, what happens is, supposedly I'm shading inside part of the circle. There can be two cases. One in which the boundary of the circle is also included. So which means that the equation of the circle would have been x squared plus y squared less than equal to r squared. Since the boundary is also included, when I take any 2 points, I could have taken points this and this joined by the line segment, and it would have lied completely within my set. So it would have been a convex set. But here, because boundary is not included, only the area inside is included. So my equation is this. Now, I am taking any 2 points, joining it with a line segment, but these 2 points are not within the set. They're outside the set. And since they're outside the set, this is not a convex set. We have a complete mathematical proof for this also. But usually, for sets to be convex sets, the boundaries have to be inclusive in the shaded regions. Only then they become convex. Now, here for us, it is important because we just want to talk about indifference curves. So, for example, I tell you that I am interested in the region in which a consumer weekly prefers a bundle. Now, weekly preferring a bundle. So if a bundle A is weekly preferred to a bundle B, then I'm saying that this is the equation. This is what we did yesterday. So this comes down to 2 parts. Either I'm indifferent between A and B, or A is preferred over B. This is a weakly preferred set. There can be 2 possibilities. So if I'm indifferent between 2 bundles, it will be on the indifference curve. If one bundle is preferred over the other bundle, it will be all the bundles which are above the indifference curve. So weakly preferred sets will either have bundles which are on the indifference curve or above the indifference curve, including the indifference curve, because it's a weakly preferred set. I am including the indifferent bundles also. Now the question is this convex set? You can try it. Take any 2 points, join it with a line segment. This line segment lies within the shaded region. So yes, it is a convex set. You can take any 2 points wherever you want. Join it with a line segment. It will lie within the shaded region. So that is why it becomes a convex set. This is very, very important for me to do an important BSc question, which I will do next week. But they will clearly, one of the option will clearly say, or one of the option just says that it is a convex set. The other says that there are horizontal lines, vertical lines. It's a very, very important and famous question for BSc. So I will be using this property of convex sets. So it becomes important. Any bundle which lies in the shaded region, if I can draw a line segment through the shaded region, it becomes a convex set. Now, I have a question here which you have to think and answer. I'm taking a dot. And I'm asking, is this dot a convex set? This is the kind of question they will ask in DSC from microeconomics. So we are taking this dot, and I'll tell you where to use this. But just for now, is this dot just this discrete dot, is it a convex set or not? What do you think? Give any try. Give it a yes or a no. Just think about it. Give it a try. Okay. Okay. Now let's see. So it is